Hello students, I am going to explain about second part of work energy theorem, and previously I have explained about the effect of zero force, work energy, and effect of zero force, and what will happen if two opposite forces act on the object, what will be the effect on the position of the object, etc. All those things discussed, very basics essential to understand the work energy theorem are discussed in the part 1. In the part 2, I am going to explain about work definition, and also how to understand work energy theorem. See, you all know very well that at least very know that you know the very well that work is equal to force into displacement into cos theta. That is what even high school students up to high school students of standard 9th class might have known. Okay, here I have shown a diagram here. An object is placed at position A on the ground or floor, etc. A force is applied on the object, thereby the at that point the object is assumed to have initial velocity. See, when the object is at A, the object is assumed to have initial velocity u, and at the same time a force is applied on the object. Okay, the force is applied continuously, thereby the object has reached point B. At that point also still the force is F, but the velocity of the object is V. Once the force is applied, the object acquires acceleration, because F is equal to ma. By Newton's second law, you all know that F is equal to ma. Therefore, once the force is applied on the object, the velocity of the object will change or will increase with time. Suppose if the velocity is u at point A, definitely at point B the velocity will not be u, but it will be v, unless some other conditions are placed. So when force is applied, the body acquires acceleration, and so here also the body velocity is increasing from u to v. During this change, the object has covered a distance of d. So work is equal to force into displacement into cos theta. By introducing such definition, we are able to solve many problems of physics. Okay, what is the use of work energy definition? By defining work is equal to force into displacement into cos theta, we are going to get some more concepts, say kinetic energy and potential energy concepts, and these concepts helps us to solve many different varieties of problems, variety of problems of the practical world. Okay, that is why we are introducing the definitions, say work, energy, etc. Okay, the purpose of these definitions are all to solve the practical world problems. Okay. That you can see once you solve some problems after the end of this section. Okay, you can understand the practical world problems after the end of the discussion of this topic. Okay, after discussion of this topic, we can solve some practical world problems. There you can understand how these concepts of work and energy are going to be very useful to solve the practical world problems. And see, work is equal to defined as force dot displacement, that is scalar dot product of force and displacement. And force and displacement are vectors. Vector products, vector multiplication is two types. One is dot product and cross product. Here we are using dot product. So F bar dot D bar is equal to F bar magnitude D bar magnitude into cos theta. Theta is the angle between force and displacement. In the figure shown, the displacement is along the direction of the motion of the object. See that, along the direction of the force is towards right direction, displacement is also in the right direction. So force and displacement are in the same direction. When they are in the same direction, the angle between them is 0. Therefore, if theta is equal to 0, that is if force and displacement are in the same direction, then f bar dot d bar is equal to fd cos theta is equal to fd. F bar dot d bar is equal to fd cos theta, and cos 0 is equal to 1. So f bar dot d bar is equal to fd cos theta is equal to fd. That is see, once you confirm that when the displacement and force are in the same direction, the definition of work results in force into displacement. Simply force into displacement if the force and displacement are in the same direction. But at the same time, let us apply Newton's second law. Newton's second law says that force is equal to mass into acceleration. Mass into acceleration. And also, you know very well that if the force is constant, acceleration will be constant. If the force is constant, acceleration will be constant. When acceleration is constant, you can use the formula, say v square minus u square is equal to 2as. V square minus 2as u square is equal to 2as. Why? Because only this formula, because in this formula there is acceleration and displacement. Acceleration and displacement, the definition of work involves displacement. So this formula is useful. Remember that this formula is valid only when acceleration is constant. Acceleration will be constant only when the force is constant. So we are making some implicit assumptions. The assumptions that force is constant, thereby acceleration is constant. So you can use v square minus u square is equal to 2as. V square minus u square equal to 2as means a is equal to v square minus u square by 2s. V square minus u square by 2s. And here display s is equal to displacement d. S is equal to displacement d. So you are substituting in place of s d. Then this formula becomes a square is equal to v square minus u square by 2s is equal to v square minus u square by 2d. So work is equal to force into displacement. Force into displacement is equal to mass into acceleration into displacement. In place of f you are writing m into a, and in place of a you are writing v square minus u square by 2d, and that is again multiplied with the d. So this d and this d will be cancelled. This d will be cancelled, and so it becomes m into v square minus u square by 2. M into v square minus u square by 2, and that multiplication results in half mv square minus half mu square. So finally the work is equal to half mv square minus half mv square. That is what we derived, and this quantity half mv square is final kinetic energy, half mu square is initial kinetic energy. So half mv square minus half mv square is equal to final kinetic energy minus initial kinetic energy, that is equal to change in kinetic energy. So in this way finally we confirmed that work is equal to change in kinetic energy. That is so work is equal to half mv square minus half mv square, or work is equal to change in kinetic energy. That is what here also displayed. Work is equal to half mv square minus half mv square, or work is equal to change in kinetic energy. I am showing an example of work done with numerical values. Now I am showing one example with numerical values. See, you consider a case, a big room is there, the room is tightly bounded and tightly closed, and there is a water in the room. There is a water in the room from one end to other end, and there is a raft, a small boat like structure. On the raft a man is standing, and that man applying a force of 10 newtons towards left. A force of F1 is applied on the wall towards left. By Newton's third law, the wall also applies a force of 10 newtons in right direction, that is F2, in right direction. So by F2 the raft will move. The raft will move from one end of the room, see, from this end to this end, and in the process the raft has covered has made a displacement of 10 meters towards the right. So here I want to ask you, what is the work done by F2? F2 is 10 newtons exactly at the point P, when the man applied a force of 10 newtons towards left, and by that the raft itself has moved from one end of the room, say left end of the room, to right end of the room. In the process the raft had made a displacement of 10 newtons. Okay, force is 10 newtons, displacement are 10 newtons. Force and displacement here F2 and D are in the same direction, so angle is theta is equal to 0, cos 0 is equal to 1, so work done is equal to FD F2 into D is equal to 10 into 10 is equal to 100 newtons. This is what most of the students, almost 99.99% students will say work done is equal to 100 joules. Work done is equal to 100 joules, but it is wrong. Actually, here the work done is equal to 0. Here the work done is equal to 0. Why? Let us see that. See that in the definition of work energy theorem, the force should be applied continuously throughout the displacement. See that. In the work energy theorem, the force of 10 newtons, this 10 newtons should be applied on the raft throughout its displacement from left end of the room to right end of the room. Throughout the journey, the force should be applied. But here, what is happening is the force of F2 of 10 newtons is applied only at the point of P when the man is applying a force of 10 newtons on the wall. After that, the raft will drift towards right. Once it is drifted towards right, the man is no longer applying a force on the wall. So wall also no longer applies any force of F2. Okay. Once raft drifted towards right, the man no longer applies a force on wall, and wall also no longer applies a force of F2. So that is force F2 is disappearing immediately once the raft makes a small displacement from the wall. There is no force of F2 after raft just glided away from the wall, and the raft by itself has moving from left end of the room to right end of the room. How it is possible? See that the water is frictionless surface. The water is standstill water, and so it is frictionless surface. Like that we can assume. And when there is a frictionless surface, by Newton's first law will say that if there is no force and if the surface is frictionless, the body continues to move without any force. That is what Newton's first law. What Newton's first law say that if a body is on a frictionless surface and if there is no force on the object, the body continues to move in uniform motion. Uniform motion means moving in a straight line with a constant velocity without any force. That is happening here. Once contact between hands of the man and wall disconnected after the raft moves slightly towards right, the raft itself moves from left end of the room to right end of the room without any force, but it is making displacement. So work done is 0 because work done requires force into displacement. Force is 0 but displacement is there, and so force into displacement is equal to 0. That is why here this example will give us a clear idea into the work energy theorem, and this example stresses that the force in the definition of work and force in the definition of work, that is force into displacement, the force should be applied continuously. Without any break as long as object is making displacement. This is what I want to remind you to remember whenever you are applying work energy theorem. Thank you. I am concluding now.